Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be doing Unit 12, Lesson number 1 on Introduction to Probability. Unit 12 is all about probability, and probability is one of the most slippery topics in all of mathematics. Some people don't even believe it's true math, right? The idea of trying to quantify chance or the likelihood that something's going to happen. And yet we do it all the time. Hey, I toss a coin. What's the probability it lands on heads? 1 out of 2, or 1/2. So probability is one of those topics that it is very important to understand the terminology and understand the way to look at it step by step to really build the mechanics up so its slippery nature is a little bit easier to get a handle for. Anyway, let's jump right into it. One of the important things about probability is the kind of terminology that gets used. And although I'm not really huge on vocabulary, I think understanding what these words mean is quite important. So let's take a look at some of them. All right. One of the things you're going to hear a lot is an experiment. Now, I know when I say experiment, a lot of people basically think, mad scientist, beaker, liquid, pour other liquid in, etc. It's an experiment. But in probability, an experiment is just any process, anything that happens. Like, hey, I'm going to flip a coin 5 times. That's the experiment, right? So an experiment is any process, anything that happens whatsoever that has well-defined outcomes. So let's talk about what an outcome is. An outcome is a result from a single trial of the experiment. So, I got this experiment, I'm going to do something. So I do it and I say, hey, that was the result, right? That's the result, and that is an outcome. Let's talk about what an event is. An event is a collection of one or more outcomes. In other words, an outcome is just what happens from the experiment, but an event could be a collection of one or more outcomes. And finally, a sample space. The sample space is the collection of all the outcomes of the experiment. A collection of all the outcomes of an experiment is known as the sample space of the experiment. So all of this terminology we're going to be using all the way throughout this unit, and I'll keep kind of reviewing what it means and how to get a feeling for it as we work through problems. But let's do exercise 1, where we're going to get a little bit of use of this terminology. So in exercise 1, an experiment is run whereby a spinner is spun around a circle with 5 equal sectors that have been marked off as shown. Okay, fair enough. Letter A, what is the experiment? Well, this is very easy. Spinning the spinner. That's the experiment. That's the whole thing. Letter B says, give one outcome of the experiment. Well, one outcome would be it lands on the number, let's say 5, right? That's one outcome of the experiment. You could pick any number, 1 to 5, right? Lands on the number 5. Letter C, what is the probability of spinning the spinner and landing on an odd number? What is the event here? What outcomes fall in the event? Well, I bet you know enough about probability to answer at least the first question. If I spin that thing, what is the probability that the spinner will land on an odd number? Think about that for a minute. Now, a lot of people will say 3 out of 5. Okay, so let's talk about events. Remember, events are collections of outcomes. The outcomes are 1, 2, 3, 4, 5. The event itself is landing on an odd number. Don't get me wrong, an event could also be an outcome. So you could say, well, the event is landing on a 5, right? And that is also an outcome of the experiment. But very often events include more than one outcome. The event is landing on an odd number. Very often events are symbolized with a big capital E or other capital letter, And it says, well, what outcomes fall into this event? Those are the outcomes 1, 3, and 5. Those are all the outcomes that land. So the probability of landing on an odd number is 3/5. 3/5. Okay? Now, if you said something like 3 out of 5, that would also be okay as well, but we're going to talk about why we want probabilities expressed as a number. Expressed as a number. And that number could be a fraction, it could be a decimal, it could be a percent, but we're going to try to avoid writing actually answers like 3 out of 5. We might say it, so I might write down 3/5 and then say, well, the probability is 3 out of 5. There's nothing wrong with that. But when we actually write down the numerical value of the probability, we want it to be a number, like 3/5. All right, well, pause the video now and think about this a little bit. Okay, we're going to clear it out. It's been many, many years since you've really worked with probability in math classes. Don't get me wrong, it could be the case that you had a geometry teacher last year who brought a little probability into geometry, but most likely you haven't seen geometry since maybe even 7th grade. And yet the basic definition of probability is something that we saw in the last problem. It says the probability of an event E occurring is given by the ratio PE, kind of looks like function notation, equals N of E divided by N of S, where N of E is the number of outcomes that fall into event E, and NS is the number of outcomes that fall into the sample space. All right? So the probability is always the ratio of how many outcomes fall into the event that we care about, divided by how many total outcomes that there are. So in that last problem, there were 3 outcomes that fell into the event of being odd. There were 5 outcomes that were in the sample space, because the sample space is everything. So our probability was just 3/5. 3/5, which, if you wrote it as a decimal, would have been 0.6. And if you wrote it as a percent, would have been 60%. We could say, the probability of landing on an odd is 60%, or 0.6, or 3/5, or even 3 out of 5. All right, well, pause the video now if you need to and write down any of this stuff, including the correction on the word event. It shouldn't say the probability of an even E. It should say event E. All right, let me clear it out, and let's keep going. So, exercise 2 says, given the above definition, which I've got just written there, between what 2 numbers must all probabilities lie? Explain. Now, this is very important because, again, a lot of people think of probability as 2 out of 7, 3 out of 5, 10 out of 11. But probabilities are numbers, and they all lie between 2 numbers. What are they? Think about this for a little bit. All right, well, all probabilities, let's take a look. Think about this for a minute. I'm going to draw what's known as a Venn diagram. Let's say that this is the sample space S. And let's say this is event E. Okay, and let's say all these dots represent outcomes. Right? And so, of course, we count the number that are in here, we count the total number, we divide, and we get that. Well, the smallest that N of E could possibly be, the minimum that N of E could possibly be is 0. And the maximum value for N of E, remember, N of E just stands for the number of elements in E. The maximum that could be is the number of elements in the sample space, if like everything in there lied within E. So that means that the minimum probability would be 0 divided by the number of elements in the sample set, but that's just 0. That's the minimum that your probability could ever be, so no negative probabilities. And the maximum that the probability could be would be NS divided by NS, but that's just 1, right? So all probabilities must be greater than or equal to 0, and you could certainly have a probability of 0. The probability that I'm going to play in the National Basketball Association is zero. The probability that I'm a math teacher is 1. All right. Now, some people might say 0 to 100 because they're thinking about percent. And I wouldn't disagree with that. But most of the calculations that we're going to do using probabilities are going to be in their non-percent form. So I would encourage you to start thinking right now in terms of probability being between 0 and 1, with a probability of 0 being very unlikely, maybe even impossible, and a probability of 1 being something that is guaranteed, something that will absolutely, positively happen. No question about it. So, pause the video now and write down anything you need to. All right, I'm going to clear out the text. Let's move on to the next problem. Theoretical probability. So there's two types of probability that we're going to see today. One's called theoretical and one's called empirical. All right, they're both amazingly important probabilities. Theoretical probability, though, is probability that you can really figure out without running any experiments, without doing any kind of like trials or anything like that. I don't have to go out and do a survey to figure out theoretical probability. Theoretical probability can just be done by thinking about how many events are in the sample space and how many events how many outcomes are in the sample space and how many outcomes are in the event we care about. So let's take a look at one that's classic, right? Flipping a coin. Exercise number 3 says a fair coin is flipped 3 times. Okay, so that's the experiment. Not flipping it once, but flipping it 3 times. And the result is noted each time. The sample space consists of ordered triples such as H, H, T. The reason that we call them ordered triples is that the order matters. In other words, HHT represents H on the first throw, H on the second throw, and T on the third throw, right? Which is what we've got right here. Letter A asks us to draw a tree diagram to show all of the different outcomes in the sample space. Tree diagrams are a nice way of visualizing outcomes of, let's say, more complicated experiments. And this is how they work, okay? If I was going to do this experiment, the first thing I would do is flip the first coin. And the first coin could turn out to be either a head or a tail, okay? So if you will, that's my first flip, okay? But let's say I got a head on that first flip. Then I would flip the coin again, and I could get a head or a tail. All right, that's really my second flip. Now I would do the same thing if I got a tail on my first flip. I could flip again and I could get a head or a tail. Now before we flip it a third time, just understand this HH, right, walking along these branches of the tree, HH represents getting a head on the first and then a head on the second. This one, HT, represents getting a head on the first flip and a tail on the second flip. This TH, even though they both have an H and a T, is a completely different outcome, right? That's getting a tail on the first flip and a head on the second one. Anyway, let's add the last one, the third flip. Okay, on the third flip, right, assuming I got a head and a head, I could then get a head or a tail. Assuming I got a head-tail, I could then get a head or a tail. And likewise a head-tail and a head-tail. Letter B says, list all the outcomes as ordered triples. How many are there? Well, here's one, head, head, head. Right? Or I could have gotten a head, and a tail. Or I could have gotten a head, a tail, and a head. Or I could have gotten a head, a tail, and a tail. And by the way, those 4 are all of them where I got a head on the first throw. Then I could go with the ones where I got a tail on the first throw. So I could have gotten a tail, a head. Or I could have gotten a tail, a head, tail. Or I could have gotten a tail, tail, head. Or I could have gotten a tail, tail, tail. And how many are there? There are 8. So there are 8 total outcomes in the sample space. 8 total outcomes, right? There they are. You can also figure out how many outcomes are in a sample space by a tree diagram by counting sort of the final branches. So 1, 2, 3, 4, 5, 6, 7, 8. 8 total things. Now, letter C says find each of the following probabilities based on your answers to A and B. Well, the probability of all heads. Well, that means I would want the number of outcomes that represent all heads divided by the number of outcomes in the sample space. Well, there's only one that is all heads. That's that one. And yet there are 8 in total, so the answer is 1/8. Letter 2 says exactly 2 heads. Well, there's this one that's got 2 heads. There's this one that's got 2 heads. And there's this one that's got 2 heads. So there are 3 that fall into that event, and there are 8 total. So the probability is 3/8. Now, how about the probability of all heads or all tails? Think about this for a minute. Well, or implies inclusiveness, right? So we've got this one that's all heads, and this one that's all tails. There are 2 of them that fall into that event out of 8, which of course could be reduced to 1/4, which is 25%. Now, what's interesting is if you took a coin and you flipped it 3 times and it turned out to be tail each time, you might step back and go, oh my gosh, that's amazing. That's not very likely. And yet you have a 25% chance that if you flip a coin 3 times, it's going to land the same way all 3 times. Now, there's only a 1/8 chance that it'll land on tails all 3 times. But you would have been amazed had it landed on all heads or all tails. And yet, there's a 25% chance of that happening. All right, pause the video now and write down anything you need to. All right, let's clear this out. Keep going. Empirical probability. Now, empirical probability is probability that's derived from running an experiment to determine the number of outcomes that fall into a particular event. This is probably the way more common probability. Don't get me wrong, theoretical probability still comes up a lot. If you've ever seen somebody play a lotto game, they'll say something like, "Wow, you have a 1 in 350 million chance of winning the lottery." Well, that's theoretical probability. They can calculate that. On the other hand, let's take a look at this empirical probability problem. Exercise 4 says a survey was done by a marketing company to determine which of 3 sodas was preferred by people in a blind taste test. The results are shown below. Letter A says find the empirical probability that a person selected at random from this group would prefer soda B. Express your answer as a fraction and as a decimal accurate to 2 decimal places, and that's kind of the standard. Well, again, we have the same thing that we always would have, which is that it's the number that fall into, I guess, event B divided by the number that fall into the sample space. Event B has 24 outcomes, 24 people that chose it, out of 53. Now, if we actually did 24 divided by 53 on our calculator, that would be 0.45, rounded to 2 decimal places. Okay? Now, of course, a lot of people like probability as percents, and that would be 45%. But I want you to keep in mind that all 3 of these really are different ways of showing the same thing. All right? Now, letter B, find the empirical probability that a person selected at random from this group would not prefer soda A. Would not prefer soda A. Again, express your answer as a fraction and a decimal place accurate to 2 decimal places. Well, the people who don't like soda A are the people who like soda B and soda C. So, if you will, the people that fall into the not A category, divided by the total, will be 24 plus 11 divided by, 53. And that'll be 35 divided by 53. Yeah, still right. And as a decimal, That's 0.66, or 66%. It's pretty rare that we'll express probabilities to a greater degree of accuracy unless they're really small. If the probability was like less than 2%, less than 0.02, then we might take, some additional decimal places. All right, pause the video now and write down anything you need to. Okay, let's zap it. So in today's lesson, we introduced probability, the terminology about probability, and the fundamental idea that we calculate the probability of an event by finding out how many outcomes fall into that event and dividing that by how many outcomes are in the entire sample space. That's, of course, the key to doing almost all probability problems, and we're going to be using it a lot in future lessons. For now, I'd just like to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.